Good morning, everyone, and thanks, Fergus. I'm really pleased to be able to kick off our symposium today with a presentation on geohole spacing analysis. I like to call it everyday DHSA because it's snappy. Firstly, I want to apologise to those of you in the room for whom this material is familiar. I do like to start things at the beginning, and I feel if we all become proficient at drill hole spacing analysis, it can be used as a useful tool to assist ensuring our projects are well informed and to help quantifying uncertainty in the development of a project, from that first conceptual model through to grade control. So what is drill hole spacing analysis? It's a process that assesses the theoretical estimation quality for a given drill spacing. And the best thing is that that drill spacing doesn't actually need to exist. A drill hole spacing analysis can inform drill program design requirements for resource definition and grade control drilling. It can be applied in the early stages of a project to assist budgeting. Drill hole spacing analysis can help in quantifying the value of gathering more information relative to the reduction in risk of a project. Drill hole spacing analysis can support mineral resource classifications in a simplistic way. So why are drill hole spacing analysis so popular? Drill hole spacing studies are really project specific. They use your data in the variogram modelled from your geological interpretation in the analysis. The results from a drill hole spacing analysis are objective. The process is repeatable and auditable. It can optimise your drilling required to advance a project, and drill costs can be linked to enable assessment of cost versus risk relationship. And they can, to an extent, quantify uncertainty. Drill hole spacing studies can be used in exploration to define spacing required to upgrade classification. They optimise expenditure and they can help you prioritise your targets. During production, they can propose grade control drill spacings required to capture possible short-term variabilities or meet production targets. And they can be used to check and support your classification decisions. So there are three main types of drill hole spacing analysis, and they increase in complexity as we go along. Estimation quality studies are a simple analysis of kriging efficiency or slope of regression for different simulated drill spacings. Production-linked studies, or the 90-15 approach, utilise assumptions regarding production scales and can consider risk with the application of error margins and confidence intervals. And simulation methods can quantify uncertainty of estimates, providing probability distributions and considering local variability and support effects. So the estimation quality approach. This is the simple analysis of kriging efficiency or slope of regression for different simulated drill grid spacings, and these are what I call everyday DHSA. In this approach, theoretical estimates are undertaken at different spacings and compared, particularly the slope of regression and kriging efficiency at each drill grid spacing. These studies use project-specific variograms, and as such, the results are influenced by the quality of the variogram. It's important to understand that your drill hole spacing analysis results may change with more data. So undertaking frequent reviews of your variogram and resultant DHSA are important. The drill spacing that you define as measured may change with a greater understanding of the deposit and as you infill your data distribution. Snowden Supervisor has a workflow which makes undertaking an estimation quality DHSA really easy. I'll step you through the key inputs and outputs of this workflow later in this presentation. So the production-linked or 90-15 approach is a result of a drive for better practices of resource classification across the different global reporting codes, and it was developed by Harry Parker and his colleagues. The approach uses the estimation variance from large block sizes informed by a variety of different drill grid spacings Similar to the estimation quality study, it also uses project-specific variograms. The 90 represents the 90% confidence interval of a normal distribution, and the 15 represents 15% relative accuracy. The block sizes should be equivalent to annual, quarterly, or even monthly production, depending on the level of study. So your measured resource would apply a quarterly or a monthly production block size, and an indicated resource is equivalent to an annual production block size. So this approach is more sophisticated, but it still doesn't consider issues such as geological or metallurgical that might downgrade the resource, and it is more appropriate for large-scale production scenarios. And the simulation approach, I'm not going to go into this because Ian has a presentation just before lunch and I don't want to steal any of his thunder, so you just have to wait until then. So, application to mineral resource classifications. I've alluded to thresholds regarding confidence intervals and relative accuracy with respect to the 90-15 approach. And this is probably our best practice in industry. So, a drill hole spacing analysis can go some way to quantify confidence in your project and ensure discussions of criteria are met with regards to the reporting code requirements. It's still important to consider in classification the geometry of your ore body, your geological confidence and continuity, your drilling methods, your drill hole sampling and spacing, your data integrity, your spatial correlation, estimation methodology, density, mineralogy, and geometallurgy. So DHSA is not a solution alone to resolve these classification issues. There are some limitations to drill hole spacing analysis studies, and that is you're always limited by your inputs, and in this case it's the variogram, and by definition your domaining and interpretation. So drill hole spacings defined in the study may have to be further adjusted for other geological phenomena that you encounter, like faulting or folding. And these studies are based on models and estimates, and as such they should be seen as indicative. So let's move on to Snowden Supervisor. So once you have declustered and top cut your data, you've modelled your variogram, you can input or you can insert a grade controlled DH spacing analysis at the continuity model level. There are two main tabs which you can modify to get your simplistic drill hole spacing analysis going. The first is the drill hole spacing parameter, and in here your various inputs are costs. Now you don't have to input costs. Supervisor is not a drill planning tool, and so the costs that will be output here are relative to the grid spacing, so it doesn't take into consideration your existing drill grid. If you want to have accurate costs and if you want to have a planned drill program, you need to use a different tool, perhaps like Studio RM Pro and the drill hole planning tool in there. So you can input your drill hole orientation, so you can undertake drill hole spacing analysis on any orientation deposit or domains. Your search, your optimal search ellipse, sorry, I can't really see it. So your optimal search in each direction and your drill hole grids. So you can put in parameters of your range of drill hole grids for your grid definition, or you can manually input those. The second tab that you would like to review, you can define a block centroid and your block size. Here I've got my my resource estimation block size, so 25 by 25 by 5. You input your search angle, which you can use from your continuity models that you've already developed, or you can overwrite this, your search ranges. You can overwrite or use your, again, use your previously defined ranges in your continuity models. Minimum and maximum samples, your maximum samples per hole. And then there's also this multi-block option. So a multi-block is depicted in the top right-hand image, where I've got hundreds of little blocks. And so a multi-block DHSA would analyse the creating efficiency and slope of regression for each of those blocks. So you will have a range of options and results for a multi-block DHSA. So that will include blocks on your margin which will perform less well than blocks right in the centre of your deposit. So your outputs from Supervisor include a number of graphs. So you've graphed your creating efficiency and slope of regression, which is this graph here, your negative weights, and your relative costs. And also it tabulates all of the options based on the drill grid spacing. So when you're selecting an optimal block size from this everyday drill hole spacing analysis, you would choose a block size where, so this is our broader spacing to the right, our finer space drill spacing to the left, and you would choose a block size where your improvement in creating efficiency and slope of regression starts to plateau. It's also good to cross-check your costs. Obviously, there'll be incremental increases with a finer drill grid spacing. So you don't, you obviously need to choose a spacing that has realistic costs associated with it. So I'm going to move on to a case study of a drill hole spacing analysis I completed earlier this year. Thank you to APAC Energy for allowing us to use some of their data in this presentation today. And we were to recommend a measured drill spacing for the Wilconi nickel cobalt laterite. So the Wilconi deposit is located 700 kilometres from Perth, near Wiluna, in the northern part of the Norseman-Wiluna greenstone belt. The mineralisation has developed through lateritisation of the ultramafic perseverance sequence, and it's concentrated in the saprolitic clays overlying the ultramafic rocks. The deposit's approximately 20 kilometres in strike and 1.5 kilometres wide. The nickel mineralisation varies in thickness up to 30 metres, but averages 4 metres, and the cobalt is further enriched in the upper portion of the saprolitic clays. So our objective here was to recommend drill spacing required to quote measured resources for the project. And our summary approach was to undertake a kriging quality DHSA. We were going to utilise domain 5001 parameters, which we considered the worst variogram. So domain 5001 was a lower grade nickel domain that encompassed the higher grade central core. We generated pseudo drill grids to reflect 10 by 10 up to 250 by 250 drill grids. And then we also checked the 90-15 production linked approach. And we used Supervisor in all these cases with a tiny amount of Excel post-processing. So as I mentioned, domain 5001 defines a lower grade nickel halo surrounding the higher grade mineralisation. And we chose our worst variogram because what we defined there would still be appropriate for the best variogram in the deposit. So by choosing the worst variogram, the drill spacing that you define from that meets criteria for the better ones. And data was constrained to an area in the south that was currently classified as indicated. You can see the search ellipse. We had a flat search with quite a decent range out to 350 metres, oriented slightly north-northwest. So the kriging quality drill hole spacing approach, we had our grids defined, and we graphed the kriging efficiency versus drill costs. On this side, again, that's a relative cost. And we selected the optimal spacing where the improvement of the kriging quality plateaus. And we selected a drill spacing of 50 by 50. And again, that was so approximately 80 to 82% kriging efficiency and not a huge cost. So yeah, 50 by 50 grid spacing defined by the Cregan quality drill hole spacing analysis. So in the 90-15 production linked approach, again, we used the same drill grids or the same range of drill grids, but we increased the block size to represent a quarterly production volume. And we took quite a simplistic approach here. It's a really big, fat deposit, so we could just plonk a block in the middle of it. But if you've got a different sized deposit, you may need to have a different shaped polygon, but we could get away with using a big block. In Supervisor, we needed to convert our percentage nickel mineralisation to ppm because we needed to see those significant figures when we looked at the Cregan variance. And we also used a huge number of samples to offset the impact of skewed deposits. So the 90-15 approach assumes that you've got a normal distribution. So you can get some errors when you have skewed distributions of mineralisation. And so huge number of samples, like 2,000 as your maximum number of samples, somewhat offsets that. And we had discretisation points every 25 metres. And in Supervisor, the same outputs. We have a cost versus kriging efficiency graph. We have the kriging efficiency and slope of regression. And in this case, we did choose a single block rather than a multi-block analysis because our block size was huge. So we just have a single point. So we needed to do some post-processing to undertake or calculate the confidence intervals. So we take it into the kriging variance into Excel and graphed our grid spacing results. So here is our 15% line of our 90% confidence interval results for each of those drill spacings. And again, so we got a 50 by 50 or a 60 by 60 grid spacing as a result there. So it's nice that the two processes spoke to one another, but it also is really important to take a reality check. And you don't want to work in isolation. So a quick Google search or chatting to colleagues about what other similar deposits have used reflects that a 50 by 50 is appropriate for a measured drill spacing for a nickel laterite deposit. So in wrapping up, I'd again like to thank ACAP Energy for use of their data. I'd like to thank Anthony at Snowden Supervisor for answering my possibly silly questions on occasion. Ian for his fanatical attention to detail. And my small people, because today's their birthday and I'm in Perth presenting and they're at home. Thank you.
Any questions, anyone? One question up back there, Claire.
Thanks, Jane. What are the key assumptions when you're working with DHSA?
What are my key assumptions? Oh, gone blank now. I thought I said no questions, Claire. You need to have a really quite robust variogram, and bringing that back to your geology. If you don't have a good interpretation, you're never going to get a good variogram. So you do need to have a half decent understanding of your project and your project continuity to, I suppose, to decide that it's making sense. Yeah, so the key input is your variogram. And then, testing, like I've tested ridiculous drill spacings. I didn't need to test 250 metre grid spacings, but I did. But just to input a range of drill grids that make sense. I mean, I think we all understand that our lived experiences in the mining industry are huge inputs to the work that we do. Yep.
Why wouldn't you do your Google search first rather than actually checking?
why wouldn't I do my Google search first? Maybe I did. No, I mean, you enter into these projects and you do your research and, yeah, as I said, reflect upon other operations and projects that you've seen around. But yeah, it's amazing what you can find on Google about what other people have done.
Sure, but similar deposits, why when you just go straight with it?
Oh, I suppose part of it's the audibility of the process. Is like, I did a Google search and this deposit in the Philippines also used 50 by 50, and I haven't visited there, but I presume that's exactly the same. So it gives you an idea of what is reasonable, but also the process will output for you something that's reasonable. And yeah, when you, particularly in the everyday drill hole spacing analysis, it is my choice of which drill grid spacing I think makes sense. So to then also have other people's opinions as well input into that is useful.
Yeah, sorry, my question was to deal with, you said the West, I just want to understand what you meant by the West in terms of variance or data continuity.
Yeah, it was actually in terms of the nugget and the range of the variogram, and also because of the nature of the domaining. So that was like a donut around the higher grade. So it was a lower grade halo around the higher grade mineralisation. So it had a higher nugget and it had a shorter range. So in choosing that variogram, we ensure that the drill spacing that we select will be appropriate for better variograms, so with a lower nugget and a longer range. And because it surrounds it, it's hard to differentiate the two. So you can't do one drill spacing for the higher grade, better behaved mineralisation and another drill spacing for the stuff that encompasses it. Hi.
The fix that you did with the 2000 maximum, did you try doing a long small transform and see if that deviated?
No, I didn't. It was quite a quick job. So it was quite a simple approach. And this was the first time that I had used that production scale 90-15 approach. So to try and get it to work quickly in Supervisor was probably our goal. So I didn't consider a normal score transformation.
I don't think in that situation, I don't think you'd want to do a normal score transformation anyway, because you need to create the raw variable to get a comfortable on your raw values. So,
Yeah.
Like at best, the normal score transformation allows you to get a variable. If you have a variogram anyway,
yeah. Thank you.